Okay, so first of all, how do we devise a method that deals with discontinuities? And we have already started in the last lecture that we are going to be, first of all, write down the differential equation, not in the differential form, but in an integral form. An integral form is a weaker form of the differential equation that you can derive from the actual differential form if the solution is smooth and continuous. But if you just look at the integral form, it is weaker because it doesn't assume the equation, the solution to the equation is actually continuous and smooth. Okay, so the derivation from the differential form to the integral form is the following. If you have a differential equation times du dx equal to 0, where g is the wave speed, right? G is the gu is equal to u in Burger's equation. Okay, and it's called the wave speed or the characteristic speed. It's called the characteristic speed and the wave speed because it actually is the reciprocal of the slope of the characteristic lines. So if you look at the kind of characteristic lines we have been looking before, or the characteristic lines we see in our xt plot, see the slope. So the reciprocal of the slope is actually g of u. So remember, when g is large, the slope slopes more towards the right. Okay, so that's when you have more slope towards the right, then the slope is actually smaller, right? Or the reciprocal of the slope is larger. So in some sense, the gu is actually the dx over dt of the characteristic lines. Right? Remember, the characteristic lines are the lines where the solution stays a constant, right? So dx dt is basically saying that, okay, so if I take the characteristic line, instead of plotting it in the x and t diagram, instead of treating the x as the x-axis and the t as the y-axis, if I flip the two axes and treat t as the horizontal axis and x as the vertical axis, then the slope would be the function g, the characteristic speed. All right, so this is basically the differential form of the equation. But if you are able to find a function, so the starting point of the derivation to an integral form is you have to find a function f of u such that df du, if you take the derivative of f, is actually equal to gu. Right? Usually you find the function by integrating the wave speed g, right? Okay, so if you find a function like this, then the differential equation can be written as du dt plus partial f of u partial x would be equal to 0. So for Burger's equation, my f of u would be equal to u squared over 2 for Burger's. This is because g of u is actually equal to u, right? Okay, so once you have the equation into this form, this is called the conservative form. As opposed to the original equation like this is called a primitive form of the differential equation. So this is called the conservative form because f of u is actually the flux of the conserved variable u. So if you remember, on Monday, we discussed an example of a traffic, right? U being the number of cars in a unit interval on the highway. F of u in this case, in that case, would be the number of cars passing through each point per unit amount of time. So it's the flux. Any equation written in such a form is like describing a conservation law. Okay, so the Burger's equation is basically describing a conservation law in which the speed, the wave speed is u, which means basically think of a strange traffic pattern where the density of cars can be positive or negative, and the speed of the car would actually increase as the density increases. That would be like a Burger's equation, right? If you have more cars and you move faster, of course, that's a strange case, but like that would be how the Burger's equation would describe. Any questions?
So does f of u describe the flux of u?
Yes, f of u would describe the flux of u, right? In the Burger's equation, and again, the strange traffic case, if the speed of the cars actually is proportional to the density of cars, then the unit amount per unit amount of time, the number of cars that passes a certain point would be proportional to u squared, right? Because the density is proportional to u and the speed is proportional to u. So the number of cars passing over a certain point is going to be like u squared divided by 2. Right? Well, okay. I think, right. I think in the case of the traffic laws, I think you have to say the cars. I mean, this is a very interesting distinction. I think you have to take note is that in the made-up case I'm describing, the speed of the cars would be equal to half of the density, so that the flux would be the product of the speed of the cars with the density itself, so half of u squared. But the characteristic speed would be u, and u would not be the actual speed of the cars. So it's like in physics, there is the material velocity and the phase velocity, right? And the characteristic speed would be the phase velocity. And here, the material velocity would be half of u.